Let's understand how a humanoid robot really works. A robot that can do simple real world tasks like lifting and tidying objects and also hold a conversation is not one single system. It is a stack of 6 layers. The top layers are about thinking and understanding. They are cheap and easy. The bottom layers are about moving a physical body without falling, and they are hard and expensive. The smart way to learn is to go from the top down. So let's walk through all 6 layers, one at a time. Layer 1 is language and conversation. This is the brain. The most important idea to understand is that the language model does not control the motors directly. Instead, the modern robot brain is two parts joined together. First, a vision language model takes the camera images and the spoken command and turns them into abstract meaning. Second, an action expert translates that meaning into real joint movements. Together, these two parts are called a vision language action model. Examples include OpenVLA, Pi0, and Groot from NVIDIA. The hardest part is not the model size. It is getting the right training data. Layer 2 is task planning. A robot does not learn whole tasks. It learns reusable skills, like go to, pick up, and place. Planning means choosing which skills to run and in what order to turn the current situation into the goal. This is where the brain from layer 1 acts as a sequencer. But here is the key lesson. The real enemy of long tasks is not choosing the order. It is compounding error. Each skill leaves the robot slightly off, and the next skill starts from a worse position until the whole task fails. The modern fix is to use one shared whole body controller for every skill. Layer 3 is perception. The robot has two kinds of senses. The first is proprioception, the sense of its own body, like joint angles and balance. This is cheap and always available. The second is exteroception, sensing the outside world with cameras. This is expensive and very noisy. Here is the trap that beginners miss. Perception also has a simulation to reality gap. In simulation, depth images are perfectly clean, but real depth cameras give noisy, broken images full of holes. A robot trained on clean images will fail on real ones. So engineers add realistic noise inside the simulator. A good strategy is to learn balance first and learn to see later. Layer 4 is manipulation, controlling the arms and hands to grab objects. The key concept is degrees of freedom. A simple gripper has about 1 degree of freedom, just open and close, which is enough for picking up and placing things. A dexterous hand has around 20 degrees of freedom for fine tasks, but it is far harder to control. Here is a lazy but smart insight. If your goal is just lifting and tidying objects, a simple gripper is enough. Do not buy difficulty you do not need. Manipulation is learned by imitation, copying human demonstrations. And once again, the winning recipe is to pre-train on cheap, plentiful human data, then fine-tune on a little expensive robot data. Layer 5 is whole body control and walking. This is the hardest layer. A tall, top-heavy, two-legged robot is naturally unstable and is always about to fall. The main method is reinforcement learning. The robot tries an action, gets a reward when it does well, and after millions of attempts, it learns a policy that maps what it senses to what it should do. But it cannot fall a million times in the real world. So it trains in simulation, with thousands of robots running in parallel on a single graphics card. To cross from simulation to reality, engineers randomize the physics, like friction, mass, and pushes, so the policy becomes robust. And because real hardware is never perfect, they always leave a calibration knob. Layer 6 is hardware, the motors, sensors, and frame. This is the most expensive layer and the biggest trap. Many beginners start by buying or building a robot first, and then spend all their time fighting hot motors and drifting sensors instead of actually learning. The right order is the opposite. Start in simulation, where falling is free and safe, and only move to real hardware once your policy works in the simulator. When you do reach hardware, remember that the physical world always drifts. A real clock, a real sensor, a real motor will never match the ideal numbers on paper. So you must always leave room to tune and calibrate. So those are the 6 layers. As you go down the stack, the same 4 themes keep returning. First, the brain never drives the motors directly. The upper layers set intent, and the lower layers execute it. Second, data is the bottleneck, not the size of the model. Third, the winning recipe is to pre-train on cheap, plentiful data, then fine-tune on a little expensive data. And fourth, always separate the hard problems, learning to balance apart from learning to see. Understand these four ideas, and you understand how a modern humanoid robot is built. Start at the top, start in simulation, and work your way down.